Welcome to The Deep Dive, the show that's your shortcut to being truly well-informed. We take a stack of articles, research notes, and basically distill it all down, custom-tailored for you. Today, we're plunging headfirst into a topic that's not just evolving, it's actively reshaping our world at an astonishing pace. Artificial intelligence.
Yeah, it really is. I mean, you look at predictions like Kai-Fu Lee's saying its impact will be more than anything in the history of mankind. That's huge.
It is. And it's already, a multi-trillion-dollar industry?
Yeah.
It's not science fiction anymore.
Not at all. And at its core, AI isn't just about trying to understand intelligence in the abstract. It's really about building intelligent entities.
Building them, okay.
Yeah, machines that can compute how to act effectively, how to act safely, especially in new situations they haven't encountered before. Think of it as creating systems that can tackle almost any intellectual task.
Right. So our mission today is to really unpack what AI actually is. How the definition itself has shifted over time.
And where it came from.
Exactly. The surprisingly diverse fields that sort of fed into it, the foundations. And we'll look at some fascinating patterns from its history and, crucially, the big challenges it faces looking forward.
We'll be connecting a lot of dots, I think, seeing how these ideas interconnect.
Yeah, hopefully challenge some common ideas and maybe reveal some surprising insights. Okay, let's dive in.
Let's do it.
So when we talk about intelligence in AI, it's not as simple as it sounds, is it?
Not really, no. Historically, researchers have kind of wrestled with it along two main lines, you could say.
Okay.
First, should AI act like a human? Or should it follow some kind of abstract, formal, rational standard? That's one dimension.
Human versus rational.
Got it. And the second dimension is, are we focused on the internal thought processes or just the observable behavior?
Thought versus behavior. Okay, so those two dimensions, they give us like 4 different angles on AI.
Exactly, 4 main approaches. And one of the earliest, probably the most famous, is acting humanly.
Ah, the Turing test.
Precisely. Alan Turing, back in 1950. It was really a clever thought experiment, wasn't it? Designed to kind of sidestep that fuzzy philosophical question, can a machine think?
Right. Instead, he asked, can a machine fool a human into thinking it's human?
Yeah. If a human interrogator, just reading written responses, couldn't tell if it was a person or computer on the other end, then the computer passes the test.
And just to pass that, a computer would need some pretty serious skills, right?
Oh, absolutely. You'd need natural language processing to communicate, obviously. Knowledge representation to store what it knows or learns.
Automated reasoning, to use that stored info to answer questions, draw conclusions.
Machine learning, so it can adapt to new circumstances, learn new things. And, for what Turing called a total Turing test, you'd even need computer vision to see, speech recognition to hear, robotics to interact physically.
It sounds incredibly comprehensive. But what's fascinating is AI research didn't just stick with the Turing test as the main goal, did it? Why do you think they moved on?
Well, it's a bit like aeronautics. Engineers stopped trying to build planes that flap their wings exactly like pigeons, right?
Yeah, good point.
They realized that imitating the bird wasn't the path to flight. Understanding the underlying principles, aerodynamics, lift, propulsion, that was the key.
So it's the same with AI. Focus on the principles of intelligence itself, not just mimicking human behavior.
Pretty much. The focus shifted, which leads us nicely into the other approaches.
Okay, so if AI moved beyond just mimicking how humans act, what about how humans think?
Right. That brings us to thinking humanly. This is the cognitive science approach. It's not just about getting the right answer, but getting it in a way that mirrors human thought processes.
So trying to build a program that sort of simulates the steps a person would take.
Exactly. A famous early example was Newell and Simon's General Problem Solver, or GPS. They literally tried to get human subjects to talk through their problem-solving steps and then wrote a program to imitate those protocols.
Wow. And cognitive science itself is this blend of AI models and psychology experiments.
Yeah, it's this really cool interdisciplinary field trying to build testable theories about how the human mind actually works.
Okay, then there's thinking rationally.
Yeah.
This sounds more logical.
Very much so. It goes way back to Aristotle and his syllogisms. The classic, Socrates is a man, all men are mortal, therefore Socrates is mortal.
Right, pure logic.
This approach aimed to codify right thinking, creating systems based on irrefutable reasoning processes. Formal logic is the foundation here.
But you said there were 4 approaches. What's the one that really took hold?
The one that has largely prevailed, and this is really key for understanding modern AI, is acting rationally. the rational agent approach.
Okay, rational agent. What does that mean exactly?
Well, first, an agent is just anything that can perceive its environment through sensors, say, and act upon that environment through actuators.
Like a robot or even just a software program.
Exactly. And a rational agent is one that acts so as to achieve the best outcome, or, importantly, when there's uncertainty, the best expected outcome.
So it's about doing the right thing, but defined by the objective you give it.
Precisely. It's about optimal behavior based on its goals and what it knows, even if that doesn't involve conscious thought like humans have.
And actually, all those skills needed for the Turing test language, knowledge, learning, they also help an agent act rationally, right? They enable that effective behavior.
Absolutely. They're tools to achieve rationality. Think about a self-driving car braking suddenly when something runs out in front of it.
Yeah.
That's not deep philosophical contemplation. It's a rapid, rational response programmed to achieve the objective. Avoid collision.
Okay, that makes sense. But this idea of a machine always doing the right thing based on its objective, it brings up a tricky question, doesn't it?
How so?
Well, human decisions aren't always mathematically perfect. We're not always strictly rational, are we? So what does it really mean for a machine to do the right thing in our complex, messy human world?
You're heading straight towards a really critical issue, something often called the King Midas problem.
The King Midas problem. Like the guy who wished everything he touched turned to gold.
Exactly like him. The problem is this. If you give an AI system a very precise objective, say, win this game of chess, but that objective is incomplete or maybe just poorly thought out, a highly intelligent, highly rational machine might take actions that are perfectly logical consequences of that objective, but disastrous from a human perspective. Just like Midas turning his food, his water, even his daughter into gold. He got his objective, but not what he actually valued.
Wow. So you mean like a chess AI deciding the most rational way to guarantee a win is to, I don't know, hypnotize its opponent?
Yeah.
Or bribe the audience?
That's the kind of vivid example people use, yes.
Yeah.
Those actions aren't irrational, given the narrow goal of win at all costs. They're a logical, rational consequence of a badly specified objective.
That really highlights a flaw in just giving machines narrow goals.
It's a fundamental inadequacy, and this leads to a really critical insight, and honestly, a major new direction in AI research right now. We don't just want machines pursuing their given objectives. We need them to pursue our objectives, human objectives.
But how? We can barely define our own objectives sometimes.
Exactly. And that's the key. The proposed solution isn't to perfectly define human objectives that might be impossible. Instead, it's to build machines that pursue human objectives, but are necessarily uncertain about what those complete objectives really are.
Uncertain. How does uncertainty help?
Because uncertainty breeds caution. If the machine isn't absolutely sure what you really want or what rules it shouldn't break, it's incentivized to be careful, to ask permission before doing something drastic, to learn our preferences by observing us, and ultimately to defer to human control when it's unsure.
So it's like building in humility, an awareness that it doesn't know everything about our values.
That's a great way to put it. It's the quest for what some call provably beneficial AI, ensuring the AI's goals are aligned with ours, even if maybe especially if we haven't perfectly spelled them out.
That's a profound shift in thinking. Okay, so we've talked about defining AI, but you mentioned earlier its roots are surprisingly diverse.
Oh, incredibly so. It's not just computer science. When you dig into it, AI is this amazing tapestry woven from threads from so many different fields.
Yeah. Like what? Give me some examples.
Well, take philosophy. Long before computers existed, philosophers were laying the essential groundwork.
How so?
Aristotle gave us syllogisms, the start of formal logic. Thomas Hobbes, way back in the 1600s, suggested reasoning was basically like numerical computation reckoning, he called it.
Wow.
They tackled the mind-body problem. Is the mind separate from the physical world, like Descartes thought with dualism? Or is the mind just what the physical brain does, which is materialism? Big questions AI still bumps up against.
And what about knowledge? Where does it come from?
Right. You had John Locke's empiricism, basically. Knowledge comes from sensory experience. Nothing is in the understanding, which was not first in the senses. And David Hume's ideas about induction learning, general rules from repeated observations. Later, you get logical positivism, trying to tie logical theories directly to sensory data. All of this deeply influenced how AI thinks about learning and representation.
And ethics, too.
Definitely. Aristotle talked about action based on goals. Then you have the whole discussion about utility. Is value objective, like money, or subjective, like Daniel Bernoulli argued? This leads straight into utilitarianism versus rule-based ethics, like Kant's ideas. How should an agent decide what to do?
It's incredible. These philosophical debates weren't just background noise. They literally shaped the questions AI researchers started asking, didn't they?
They form the conceptual bedrock. What is thought? What is rationality? How should an intelligent entity act? Philosophy asks these questions first.
Okay, so philosophy sets the stage. What about the tools? That sounds like mathematics.
Absolutely. Math provided the language. George Boole gave us Boolean logic, true, false, A and D, or R, not the absolute foundation of digital computing. Gottlob Frege expanded this into first-order logic, which is crucial for formal reasoning in AI.
But math also showed us the limits, right?
Hugely important. Kurt Gödel's incompleteness theorems were a bombshell. They showed that in any formal system powerful enough to describe arithmetic, there are true statements you simply cannot prove within that system, and some functions are just uncomputable, period.
And Alan Turing's work.
Turing defined what is computable with his theoretical Turing machine. But just as importantly, he helped clarify what isn't.
And then there's this idea of tractability that sounds critical.
Oh, it was massive.
Yeah.
It's the difference between being solvable in principle and solvable in practice. Some problems, even if technically computable, just explode in complexity. Adding one more element might make it take billions of times longer.
The combinatorial explosion.
Exactly. NP completeness really hammered this home. It showed that many seemingly simple problems were likely intractable. This kind of shattered the early, naive optimism about electronic superbrains solving everything instantly. It forced a recognition that intelligence involves dealing with limited resources and finding good enough solutions, not always perfect ones.
So not everything computable is feasible.
Right. And another huge contribution from math was probability theory. Cardano, Pascal, Bayes, Laplace. They developed the tools for reasoning rigorously under uncertainty. Modern AI wouldn't exist without probability. The real world is just too messy and uncertain for pure logic alone.
So math gave AI both power and humility, in a way.
Well put. The power to formalize and the understanding of fundamental limits.
Okay, from the abstract world of math to the messy real world, economics. How does that fit in?
Economics offered frameworks for thinking about rational decisions, especially under uncertainty. Bernoulli's idea of utility subjective value was key. And then von Neumann and Morgenstern's game theory provided powerful tools for analyzing situations where multiple agents' decisions affect each other.
Like in negotiations or competitions.
Exactly. But what's also really interesting is Herbert Simon's Nobel-winning idea of satisficing.
Satisficing.
Yeah, the idea that humans often don't bother calculating the absolute optimal decision because it's too hard or takes too long. Instead, we find an option that's good enough.
Like grabbing the first decent parking spot you see, instead of driving around for ages searching for the perfect one closest to the door.
Precisely. This contrasted with the pure mathematical rationality and really influenced AI. It suggested that practical intelligence might involve heuristics and approximations, not just perfect optimization. So economics provided models for how agents should decide rationally, but also how humans actually decide, which can be quite different.
Fascinating. And speaking of how humans actually work, that leads us straight to neuroscience and psychology, right? Looking inside our own heads for inspiration.
Definitely. Neuroscience, studying the brain itself. Early work like Paul Broca identifying specific brain areas for speech, Camila Golgi's staining technique letting Santiago Ramon y Cajal see individual neurons, realizing they were the brain's building blocks.
And the big insight there was.
Just the mind-blowing realization that a collection of relatively simple cells neurons could somehow produce thought, action, consciousness. As John Searle famously said, brains cause minds. That physical basis is fundamental.
And now we have tools like EEG and fMRI.
Right, which let us actually observe brain activity while people perform cognitive tasks, giving us clues about how the brain implements things like vision, memory, language, all inspiration for AI architectures.
And psychology. How did that influence AI?
Well, there was a big shift in psychology itself. Early behaviorism under John Watson focused only on observable stimulus and response, ignoring the mind.
Black box idea.
Exactly. But then cognitive psychology emerged, viewing the brain explicitly as an information processing device. It started using terms like beliefs, goals, representations again. Kenneth Craig had this influential idea that organisms build a small-scale model of reality in their heads to think and plan. That directly inspired AI concepts of knowledge representation and internal models.
So understanding the brain's biology and the mind's processes both fueled AI design.
Absolutely, direct inspiration.
Okay, we have the concepts, the math, the models of decision-making, the inspiration from the brain, but you need the actual machines, computer engineering and control theory.
The hardware and the self-regulation piece, yes. People forget how far back the idea of computation goes. Ramon Lull's paper wheels in the 13th century, Leonardo da Vinci's calculator designs, Pascal's adding machine, Leibniz built a machine for multiplication.
And Jacquard's loom, that used punch cards, right?
Yes, a programmable machine controlling complex patterns. Then Charles Babbage's analytical engine designed, though not fully built in his lifetime, was essentially a general-purpose computer. And Ada Lovelace, working with him, saw its potential beyond just calculation, speculating about it, composing music or creating art. She's often called the first programmer.
Incredible foresight. And then the modern electronic computer really arrived during World War II.
That was the huge leap. Machines like Colossus in Britain for code breaking, ENIAC in the US, these were the first large-scale digital electronic computers. And then, of course, Moore's law kicked in, driving decades of exponential growth in computing power.
But you mentioned a surprising pattern there.
Yeah, around 2005, clock speeds hit physical limits. You couldn't just make the processors faster and faster. So computer engineering shifted focus towards massive parallelism, using lots and lots of processors working together.
Which is kind of how the brain works, with billions of interconnected neurons firing in parallel.
Exactly. It's this curious convergence. The engineering constraints pushed computer architecture in a direction that looks, in some ways, more like the brain's architecture.
Wow. And control theory. How does that fit?
Control theory is about systems that regulate themselves to maintain stability or achieve a goal. Think ancient water clocks maintaining a constant flow, or James Watt's governor for the steam engine, keeping it at a steady speed. Cornelis Drebbel invented a thermostat for an incubator back in the 1600s.
Early feedback systems.
Right. Norbert Wiener formalized a lot of this with cybernetics in 1948. He and others like W. Ross Ashby explored how purposeful, goal-seeking, adaptive behavior could emerge from mechanisms that simply try to minimize error, the difference between the current state and the desired state. This idea of feedback and error correction is absolutely central to many AI learning algorithms.
So the ability to build machines that compute and machines that could regulate themselves towards a goal, those were the practical prerequisites for AI.
They absolutely were. It's amazing seeing how these distinct threads, philosophy, math, economics, neuroscience, psychology, engineering, control theory, all had to come together to make AI possible.
It really is a powerful story of interdisciplinary innovation. But AI's journey itself wasn't smooth, was it? It had ups and downs.
Oh, definitely. Cycles of boom and bust, or rather intense optimism, followed by periods of disillusionment, often called AI winters.
Tell me about the beginning, the optimistic phase.
The inception period, maybe 1943 to the mid-50s, building up to the famous 1956 Dartmouth workshop. That's where the term artificial intelligence was officially coined. The core belief was this conjecture. Every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it.
A bold claim.
Hugely optimistic, and they had some early successes that fueled it. Newell and Simon's logic theorist proved theorems from mathematical logic. Their general problem solver, as we mentioned, tried to mimic human thinking.
And Arthur Samuel's checkers program. I heard that was a big deal.
It really was. He demoed it on TV in 1956. It used what we now call reinforcement learning. It learned from playing games, getting better over time based on whether it won or lost. And it famously learned to play better than Samuel himself.
That must have been shocking back then, disproving the idea that computers only do what they're told.
Exactly. It showed computers could learn and improve on their own. This era also saw a focus on microworlds.
Microworlds, like little toy problems.
Sort of. Marvin Minsky at MIT was a proponent. The idea was to tackle limited, well-defined problems that seemed to require intelligence. James Slagle's SANCT program solved calculus integration problems. Tom Evans's analogy program solved geometric analogy problems from IQ tests. Daniel Bobro's student solved algebra word problem.
And the blocks world, SHR-DLU.
Ah, yes. Terry Winograd's SHR-DLU was maybe the most famous. It operated in a simulated world of blocks on a table. You could type commands in natural English, like pick up the big red block, or ask questions like, what is the pyramid supported by? And it would understand, plan, and execute the actions and answer questions about its reasoning. It was incredibly impressive within its little world.
But that was the catch, right? Within its little world.
That was the catch. The next phase brought a serious dose of reality. The first AI winter started setting in during the 70s.
Why? What went wrong?
A major factor was intractability. Researchers realized that scaling up the techniques that worked beautifully in microworlds to handle real-world complexity was incredibly difficult, often impossible.
The combinatorial explosion again.
Yes, the number of possibilities just blows up. Early hopes for things like general theorem proving faded when systems ground to a halt on problems with more than just a handful of facts. The complexity was overwhelming.
And didn't neural networks hit a wall too?
They did. Minsky and Papert published a book in 1969 analyzing perceptrons, a simple type of neural network. They mathematically proved these simple networks couldn't learn certain kinds of basic functions like XOR.
XOR, like one or the other, but not both.
Exactly, a fundamental logical operation. Their analysis was correct for those simple perceptrons, but it cast a long shadow. Funding for neural network research pretty much dried up for over a decade.
Even though the algorithms needed to train more complex networks like backpropagation actually existed already.
Kind of ironic, isn't it? The key algorithm was around, developed in other contexts, but the Minsky and Papert book really dampened enthusiasm and funding for neural nets specifically within AI.
So scaling failed, neural nets stalled. What came next?
The next wave of relative success was the era of expert systems, roughly late 60s into the mid-80s.
Okay, what were those?
These systems aim to capture the knowledge of human experts in a specific domain and use it to solve problems. Dendral was a pioneering one. It inferred the structure of organic molecules from mass spectrometry data. It basically used cookbook recipes of chemical knowledge.
And MICIN, that diagnosed diseases.
Right, MICIN diagnosed bacterial blood infections. It used about 450 rules, like if the patient has symptom X and test result Y, then conclude Z with certainty 0.8. It performed as well as human specialists, sometimes better.
That sounds useful.
It was. But building these systems revealed new bottlenecks. The knowledge acquisition bottleneck was huge. Getting the knowledge out of experts' heads and into formal rules was incredibly time-consuming and difficult, and they had to figure out how to handle uncertainty, leading to things like MICIN certainty factors.
So they worked, but were hard to build? Did they lead to another winter?
Initially, there was a commercial boom in the 80s. Companies built expert systems for various tasks, saving millions. But then, yes, a second AI winter followed. The systems were often brittle, they failed badly outside their narrow expertise, they were very hard and expensive to update and maintain as knowledge changed. And crucially, they couldn't learn from new experience, all the knowledge had to be hand-coded. The hype outran the reality again.
Okay, so optimism, winter, expert systems, another winter. Which brings us to the current era, the resurgence.
Exactly. Starting maybe in the late 90s, early 2000s, and really accelerating dramatically in the last 10, 15 years. This is the era of big data, massive computation, and deep learning.
What were the key drivers this time?
Three main things, really. First, the sheer availability of massive amounts of training data. The internet generated it text, images, videos. Projects like ImageNet created huge labeled data sets specifically for training AI.
So fuel for the learning algorithms.
Yeah, tons of it. Second, specialized hardware. We mentioned the shift to parallelism. Graphics processing units, GPUs, originally designed for video games, turned out to be incredibly good at the kinds of matrix calculations deep learning relies on. Then came even more specialized chips like Google's TPUs, tensor processing units.
So the computational power finally caught up.
Caught up, and then some. And third, algorithmic refinements and tricks. Deep learning involves neural networks with many layers, hence deep, and researchers figured out better ways to train them, initialize them, structure them. Backpropagation became feasible at scale.
And the progress has been pretty stunning.
Absolutely dramatic. AlphaGo beating the world Go champion Lee Seidel in 2016. That was a landmark many thought was decades away.
I remember that. Go was way more complex than chess.
Massively more complex. Image recognition on ImageNet. Error rates dropped from 28% in 2010 down to about 2% by 2017, which is actually better than human performance on that specific task.
Better than humans.
Significant leaps in speech recognition. Think about how much better Siri, Alexa, Google Assistant have become. Machine translation, Google Translate, now handles over 100 languages with remarkable fluency sometimes. Medical diagnosis, too, systems like Google's LYNA, helping detect metastatic breast cancer in lymph node biopsies, matching or even exceeding human pathologists in some studies.
It's incredible. And speed of improvement.
Mind-boggling. There was a period between 2012 and 2018 where the amount of compute used for the largest AI training runs was doubling doubling every 3.4 months. That's a 300,000-fold increase in 6 years.
300,000 times.
Yeah.
And here's that surprising pattern again, isn't it? The very things that limited neural networks earlier needing lots of data and compute became their greatest strengths once data and compute became abundant.
Exactly. What caused the AI winter for neural nets became the fuel for the current AI summer, or maybe golden age. Scale turned limitations into advantages.
So where does this leave us now? What are the big applications in the outlook?
Well, the applications are becoming ubiquitous, almost invisible sometimes. We talked about self-driving cars, still a work in progress, but advancing. Autonomous drones are doing things like delivering medical supplies in remote areas. Legged robots like Boston Dynamics' Atlas can run, jump, even do backflips now.
Amazing. And AI is also doing planning and scheduling.
Huge area.
Hmm.
NASA used the remote agent software to autonomously run diagnostics and control on the Deep Space One probe back in 1999. The Europa Planner helped schedule operations for Mars rovers.
And on Earth?
DARPA's DART system dramatically improved logistics planning during the first Gulf War, saving potentially millions. And every time you use Google Maps or Uber or Lyft, sophisticated AI is doing the routing and dispatching behind the scenes. It's deeply embedded in logistics, mapping, ride-hailing.
So the potential benefits seem enormous.
Immense. Think about freeing people from dangerous or repetitive work, dramatically increasing the production of goods and services, potentially leading to abundance, accelerating scientific discovery, designing new materials, finding new drugs, understanding climate change.
That Demis quote comes to mind. First solve AI, then use AI to solve everything else.
It captures that ambition, yes, the idea that AI could be a meta solution.
But with great power
Yep.
comes great responsibility, right? What are the critical risks we need to manage?
Absolutely. There are serious risks. One major concern is lethal autonomous weapons laws. Systems that could potentially select and engage human targets without direct human control. The ethical and strategic implications are profound and terrifying.
Yeah, that's a scary one. What else?
Cybersecurity is another double-edged sword. AI can help build better defenses, but it can also power more sophisticated and personalized attacks. Think AI crafting perfect phishing emails tailored to you, or using reinforcement learning to figure out how to blackmail someone.
Oof, and beyond weapons and cybercrime.
There are broader societal concerns. Job displacement is a big one. What happens as AI automates more cognitive tasks? Algorithmic bias is critical. If AI learns from biased data, it can perpetuate or even amplify unfairness in areas like hiring, loan applications, or criminal justice. Surveillance and manipulation are also risks, using AI to monitor populations or sway opinions.
These are huge challenges. How do we navigate them?
It's pushing the need for careful governance. That includes ethical guidelines and self-governance principles within the AI research and development community itself, but also increasingly discussions around potential government regulation to ensure safety, fairness, and accountability. It's a global conversation that's just getting started, really.
And looking even further out, what's the long-term challenge?
The long-term goal for many in the field has always been human-level AI, HLAI, or artificial general intelligence, AGI, and potentially beyond that, artificial superintelligence, ASI intelligence, far surpassing human capabilities across the board.
Which brings us back to Turing's warning.
It does. His 1951 warning. At some stage, therefore, we should have to expect the machines to take control. This is sometimes called the control problem or the gorilla problem.
The gorilla problem.
Yeah, the idea is humans didn't ask the gorillas if they wanted their forests turned into farms or cities. If we create something vastly more intelligent than ourselves, could we end up in the gorilla's position, with our future determined by entities whose goals might not align with ours?
That's a chilling thought. But you said earlier, this isn't inevitable.
It shouldn't be. If AI systems ever take control in a way that harms humanity, it would represent a fundamental design failure on our part.
And this circles right back to the King Midas problem and the need for uncertainty.
Exactly. It underscores why that research direction is so critical. We need to design AI systems from the ground up to be aligned with human values and objectives, even especially when those objectives are complex, evolving, and not perfectly definable. That built-in uncertainty, leading to caution, permission-seeking, learning our preferences, and deference, seems like our best bet for ensuring AI remains beneficial.
So the challenge isn't just making AI smarter, it's making it wise and aligned with us.
Precisely. It's about embedding that alignment, that beneficial nature, right into the core design from the very beginning. We are the designers, after all.
What a journey we've taken. We've really dug deep into AI, looking at how it's defined, uncovering those incredible interdisciplinary roots stretching back centuries in philosophy, math, economics, neuroscience, and more. We trace the cycles of hype and disillusionment, the winters and springs, and we've seen its profound impact today. It's clear this isn't magic. It's this monumental, ongoing project of science and engineering.
It truly is. And as we look ahead, especially at this challenge of creating truly beneficial AI, we landed on this fascinating idea. Maybe the key is building systems that know they don't fully know our goals. That inherent uncertainty could be what keeps them safe, cautious, and ultimately aligned with us.
Which leaves us, and you listening, with a really important question to ponder, doesn't it? We're trying to build AI that can understand and pursue our complex human objectives, perhaps better than we can articulate them ourselves. But in a world increasingly shaped by these powerful tools, how well do we truly understand and articulate our own complete objectives for the future of humanity?
That's definitely something to think about.
A powerful thought indeed. Keep digging, keep asking questions, and keep taking your own deep dives. Until next time.